yeah, I should actually say the title was changed. I think it was it's a talk I've given before. It's similar. It's a similar kind of topic, but yeah, it's actually called Fast Finality, Faster Blocks, but same idea. Basically, I'm here to tell you about first of all, like, why should we care about fast finality? How exactly are we thinking about this? Like concretely, like, you know, what do we want to do to actually get the protocol to finalize faster? How does it relate to shorter blocks? That's not immediately clear. And then, you know, why should you care about it? Like, why should stakers specifically care about it? Yeah, a quick why, I think, just to motivate, like, why is fast finality important? I think there's a few, like, clear reasons. Like, one is there's this, like, UX security trade-off that we get whenever you could either basically choose security or UX as a user. Like in this case, I can choose to wait for finality, and user might mean like actual user, like anyone doing a transaction. It might mean rollup, or it might mean app. You can choose to use finality and just wait for the 12 minutes or whatever it takes, and you're going to get great security but really bad UX. Or you could just say that you don't care about security and just use something like that, maybe like a weaker kind of method of confirmation, or like a third-party thing, like when you're bridging or these kinds of things. So essentially, you kind of put users in this in this situation where they have to choose, and they can't just get security by default. And this basically pushes them to potentially solutions that are not actually as good as the native one. And then another reason that you should care about it is not so much about the fast part, but it's more about the consensus upgrade part. And of course, we probably would do this consensus upgrade if to actually make the protocol faster. But something that we'd also get out of it is that we can actually use it as a chance to clean up like a ton of technical debt that exists in the consensus protocol. So I think, technical debt and also just like high level really get like optimal provable security properties that the consensus protocol today just doesn't have. And a quick note is that when we say faster finality, or even single slot finality, something that has been said a lot in the past, we don't actually mean that there's only finality. There's still this idea that we have today that the chain can progress even if we don't finalize. So there's this like available chain kind of blue thing, and there can be reorgs. Like here, these gray things are not canonical blocks, but they can still exist. And there's only like a prefix that is finalized. So none of that conceptually changes. Just the finalized part is supposed to like not lag behind nearly as much, basically. Just like follow much faster. And one protocol that we've discussed a lot over the last year for achieving this is 3SF, 3-slot finality. And it's what I'm going to call today an integrated protocol. And here integrated kind of goes at this level of like finality and availability. So there's like these two things that are happening in the protocol, and an integrated protocol is one that basically kind of smashes them together. Like both of them are essentially happening like at the same time in the same kind of way. And here you see this basically it looks quite a lot like the protocol that we have today in a way, except that basically every slot you have all the validators voting. So here you have this like head votes, but it's not a committee, it's like the whole validator set. And this is what actually enables you to get like finality much faster. So you essentially have this like finalizing pipeline, that's 3-slot, hence the name, where first like you confirm a block. This is kind of a technical thing that I don't necessarily need to get into. But after confirming, it can enter this finalization pipeline that in a way looks the same as today. It's just you first justify and then you finalize. You have basically 2 voting rounds of like the full validator set. And at the same time, another block can enter the same kind of pipeline. So at any given time, there's kind of 3 blocks that are trying to do the same thing at different stages. But otherwise, like everything looks quite the same as Gasper. Basically, you have like head votes, target votes, like source votes. So it's like same component, just in a way like everything is happening at the same time. Everyone is voting at the same time, so that we can get finality much faster. But there is kind of a problem with this protocol, even though this is something that like we worked on for a while and have like a really good understanding of like the security of it, like which guarantees it provides. And the problem is basically that we have this couple thing, like these 2 things like finality, availability. They're basically like, as I said, happening kind of together. Essentially just the fact that validators have to vote every slot, like all validators have to vote every slot. And this has some consequences. Like it's basically like a bidirectional dependence between like finality and block production. So one thing is that finality essentially slows down block production. So in every slot, everyone is voting. So we kind of have to wait for this like full round of aggregation in order to produce like a new block. So in a way, it's like finality is kind of the needs of finality are dictating how fast we can move, basically, in terms of block production. And this means also like we can't really have too large of a validator set, because you can't have millions and millions of validators voting every slot if you want to have blocks that have or slots that have a reasonable length. And on the other side, block production also slows down finality. So block production has its own needs. You have to propagate blocks, you have to execute them. There's some other things, like a bit more technical, that you may want to do to ensure that, for example, the next proposer is sure that they can produce a good block that's not going to get reorged. So there's some things that are happening in a slot that actually have nothing to do with finality. And they actually just end up kind of slowing down the finality pipeline and getting in the way. And to kind of visualize this, you can I think there's a missing slide. Okay, it's okay. Yeah, basically, you can think about it as, yeah, I mean, we can take basically the case study of Gasper to think about this, so the current protocol, where we essentially have like a very similar structure. We still have slots, we still have like committee voting, or like some amount of voting every slot. And you might think that in Gasper timelines are not coupled, because you have these like long epochs where finality happens, whereas slots are much shorter. But actually the timelines really are still coupled. And it kind of manifests in this way, that if you were to basically have smaller committees, this would help you with shorter slots. So you could say, okay, why do we have 30,000 validators voting every slot? Let's just have 1,000 validators voting every slot. This probably is going to let us have shorter slots. But this would mean very, very slow finality. And on the other side, you could say, okay, why do we have this, like, in a sense, still small committees? Why do we have like epochs that are 32 slots long? We could just have a bunch more people voting every slot. This would make finality faster. This would mean that block production slows down a lot. So the same exact trade-off essentially like exists in the current protocol, and the current protocol just finds like a compromise between the two. It just says, okay, one epoch being 32 slots is reasonable enough. You get like good enough finality, good enough slot time. In practice, in a sense, you get neither really good finality nor really good slot time. So it's kind of it's a compromise, but it's not a great one for either of the two sides. And yeah, 3SF doesn't really change fundamentally this trade-off. It just says, okay, let's hope that we can basically have really good consolidation, actually near perfect consolidation, having like almost down to the validator set being equal to the node count. So kind of fully getting rid of this like overhead factor. And yeah, if we assume that that's going to be the case, then we can say that, okay, instead of a committee, that can be the whole validator set. And all of a sudden, we can get much faster finality without actually creating too much of a problem for the slot time. But still, the underlying trade-off doesn't really change. Like, both sides are kind of getting in the way of each other. And a decoupled protocol is kind of a way out of this, where you can actually say, let's just pull apart these two things. We have finality, we have availability or block production. Let's just separate them. So you could say, okay, there's maybe some small enough committee size that we're fine with from a security perspective. Let's go with that. From the perspective, let's ignore finality for now. Let's just say, this committee, Vitalik at a post where he said this could be 256 validators, could be 500, it could be 1,000. We can like argue on the number, but this number would have nothing to do with finality. It would just be its own kind of independent assessment of what this number should be. And so you could have a much smaller slot, basically, because this part gets compressed. And finality could have basically its own separate timeline, where in this timeline, what you care about is just like as fast as possible, aggregating votes from the whole validator set. It's not kind of interacting with what's happening in terms of block production. Like, you're not trying to have a round of voting, then do some things that are related to block production, then another round of voting. You can just do rounds of voting as fast as they can be, basically. And then, yeah, what this looks like in terms of the, trying to compare with 3SF, you would still have this confirmation phase at the beginning. That's basically getting like a minimum level of security on the available chain. And now you enter the finality pipeline again. But now the finality pipeline is just directly kind of just going ahead with the voting rounds. And it doesn't have to kind of slow down to accommodate the available chain. And something that's kind of a recent I don't want to say discovery, but yeah, essentially like, something that we didn't know before. Like for quite a long time, we thought, yeah, it would be nice if you could do something like this, but there's problems once you try to use committees on the available chain. Like this was this key part that just didn't really seem to work. Like whenever you try to put committees on the available chain, security properties would just break, essentially. So we didn't really think that we could actually do this. But as of recently, we actually have a design that essentially achieves this, that gets like the same kind of properties that 3SF does, or whatever properties you want to write down for the kind of protocol that we want, that has this like available chain and finality component. You start with this and you define some security properties, and essentially we now have a design that actually achieves all the security properties that we would like, without actually needing this tight coupling essentially between the two layers. And yeah, basically once we have, now that we have a design like this, this enables us to do a few things. One is that basically we can just have both. Essentially, we can have the best of both worlds. We can have fast finality. We can have faster blocks, like faster than the finality timeline and faster than today, even. And basically, just both can be as fast as they by themselves can be. They don't have to kind of talk to each other and agree on, you can only be so fast as it allows, like finality doesn't have to kind of worry about how much it slows down block production and vice versa. Basically, it's both can be optimized independently. And this also means that we don't really have this hard dependency on the full consolidation of the validator set if we want to do an upgrade such as this. So before we basically always had this idea of, okay, if we do want to do this 3SF upgrade or whatever other form of this that we've kind of discussed over the years, we first need to get down to like 30,000 validators. Like for example, the amount of validators that today are voting in a single slot, maybe could be a bit more, maybe a bit less. Then there's like shorter slot times. This idea like that this is something we want to do in the future. This would also kind of put extra pressure on this consolidation process, because all of a sudden, if we have 6 seconds instead of 12, we probably would want to be even more sure that we can squeeze a whole voting round for the full validator set in there. So we basically have this like really hard dependency on getting the validator set down from like 1 million to almost maybe like 30x less or like 100x less, like more than an order of magnitude. And now in a way this goes away. Like once we're working with this kind of decoupled protocol, this hard dependency is not there anymore. What happens if the validator set is, let's say, 200,000 instead of 30,000? It's just that we finalize slower, but it doesn't actually kind of break the protocol. It doesn't mean that now we cannot do voting rounds in the basically time of a slot. This kind of finality process is happening on like a different separate timeline, and the slot time that we can support has nothing to do with it in principle. And yeah, and this also kind of means that we don't need to worry so much about putting like really strict mechanisms in protocol to ensure that there's a maximum kind of validator set size. So before we had always this worry of we have to really ensure that you cannot go beyond 50,000 or whatever the magic number is once we've made this upgrade. You can just upgrade and then some staking pool decides to split up their validators or like enter a bunch of like 32 ETH validators, and all of a sudden we're back up to like 200,000, and I don't know, slots just are not long enough anymore for a full voting round. So now this dependency kind of goes away, this worry goes away. If something like that happens, the only thing that happens is that finality can degrade, so finality can become longer. And I mean, we can put still incentives in order to kind of really try to ensure that this is not the case, but it doesn't become, it's not quite as bad of a worry. We're not really worried that the protocol is going to break or something like that. And yeah, I mean, this is maybe a bit like surprising that I'm saying this, because maybe if you knew that I was going to talk about fast finality in this crowd, you'd expect that I would just be trying to convince you to consolidate, and now it seems like the story is changing and consolidation is not really that important anymore. And well, this is not really the case. Actually, I'm still here to tell you like fast finality does matter, fast finality does need consolidation, and you should like try to think about in whatever, whether you're a solo staker or a staking pool or whatever, in what way you can try to help the network with that. And the reason is like, sure, we don't have this hard dependency anymore. We could in principle do this upgrade even without getting down to like 10,000 validators or something like that. But still, we're only going to get the benefits if actually the validator set is consolidated from the perspective of finality. If we have 800,000 validators, we're still going to finalize in a similar time as today. It's not going to all of a sudden go down by 20x or something like that. So basically, yeah, we really only get the benefits if we actually put the work. And the other thing is that in terms of thinking about scheduling protocol upgrades, this is going to be a massive effort from really every point of view. Like, the like the speccing level, testing level, at the level of like consensus devs, like trying to figure out how this transition is going to work. So there's a ton of work involved. We're only going to do this work if it's actually worth it. So we're only going to do this work if it actually gives us like real benefits in terms of finality. So still super important for everyone to think about how they can basically contribute to us getting there. How can they contribute to consolidation? And yeah, I think this is kind of an exciting time in the realm of like fast finality and this like stream of work, because I think we really realized that this is one of the really weak points, I think, in Ethereum's story. There's a lot of concern that this is something that Ethereum really does not do well, and where it really should be doing better. There's much better kind of guarantees that we can provide much faster, and so there's a lot of interest in having this happen. And we also kind of now have a bit of a better idea of how we can go about this in a way that, as I said, doesn't run into these like hard kind of blockers of like, okay, we can only do this after like 100x consolidation or something like this. So it's really kind of exciting times there, but there's still a lot of work to do. So from the protocol side, I think what we want to do is really like ramp up on this work in 2026 and really try to kind of finalize a candidate protocol and ideally specs. And from your side, from the staking world side, I think what we would basically ask is just like think how what's your strategy around consolidation. If there's any blockers that you have, try to talk to us. Try to figure out what are timelines in which we can resolve them. Like what things, even like at a protocol level, could help you. Let's talk about any IP that's on the table or will be on the table in the future, about any tooling improvements, probably even more important than EIPs. Let's basically talk to us, try to help us, help you, help the network. This is really important, and I think in maybe 2-3 years, we'll look back and see that, okay, we actually did the work and we can enjoy these great benefits. Thank you, that's all.
I see lots of hands for it. We have time for one question, so I'm going to grab this side of the room over here.
If you decouple the finalization and this whole concept basically from the epoch transition, then could you possibly get rid of all the epochs as well and just have slots coming in without any epoch transition?
Yeah, I think there might still be a reason to have some concept of epochs for example, something that shows up when you work on this like on trying to fix problems in a consensus protocol, like said very broadly, is that you have to keep track of more things than you do today. Like now, in a way, like things are a bit streamlined in the way the Beacon chain does state transitions related to consensus, but this creates problems. And I think to solve these problems, it probably would still be make sense to have some kind of sense of epochs. It's a bit hard now to explain without getting into like too many details. But yeah, I think there's probably like some things that don't make sense, like some aspect of what we do today with epochs that will not make sense, and some that will. Maybe I can say that.
Thank you. And Francesco, you'll be around for questions afterwards. I think my lesson to myself is every time that we host one of these events and we have a core researcher from the EF come, we really need to provide more time for their talks and questions afterwards. But thank you for offering to stay here. But I'll keep us going because we do have quite a lineup of speakers still yet for the day.